the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video is for linear algebra students who are going through vector spaces, and you've already gone through basically the vast majority of the content in vector spaces. Specifically, you've talked about vector spaces and subspaces, null spaces, column spaces, coordinate systems, and dimensions of spaces. We saved this last conversation for some obvious topics or things that we might have considered obvious as we were kind of wandering through the previous topics or previous subjects. And because we have adopted a lot of extra language as we've moved through this material, I want to modify a couple of our definitions. Now, we've already discussed column space, which is the vector space spanned by the columns of a given matrix A, and we've discussed the null space, which is the vector space spanned by the solutions to the equation AX equals 0. But here are some modified versions of those definitions. The column space of an M by N matrix A, written as the column space of A or col of A, is the subspace of Rm consisting of the set of linear combinations of the columns of A. Now, honestly, if you look back at your definition that you learned early on in this material concerning column space, you will see that in that definition, we did not reference the column space of A being a subspace of Rm. That was a subsequent theorem. So I just want to write these definitions out to include those theorems in the language of the actual definition. And you could read the definition, the modified definition of the null space down below if you want to. However, I'm just going to move forward. Now we talked about, again, the null space and the column space of a matrix A. We are now going to introduce something called the row space of that matrix A. The row space of an M by N matrix A, written as the row of A, is the subspace of Rn consisting of the set of linear combinations of the rows of A. And that's really nice because it really links together with our definition of the column space of A. Now, something I want to draw your attention to here is that when you're working with the row space of A, or better yet, maybe I should say when you were working with the column space of A, you had to be very careful about taking A and putting it into an echelon form. Remember, you had A, you got it into an echelon form, we'll call that echelon form U, and it turned out that the column space of the echelon form is not necessarily the column space of the original matrix. And that is because as you move things into echelon form, you could actually zero out some rows there, and therefore, while the original matrix could have generated a vector with, let's just say, a non-zero entry in its final entry, the echelon form might not actually be able to do that. And that's why when you found an echelon form of A, you would mark the pivot columns and then go back to A itself, grab those columns and say, yep, my column space is generated by those columns. Those columns form the basis for the column space of the matrix A. Now, technically, you could have just grabbed all columns of the matrix A and said, well, the column space of A is the span of these vectors. That's the lazy person's version of the column space. But we are often more interested in a basis for the column space. However, with row space, we are under no such constraints, and we'll see a theorem in a little bit that will showcase that. But it turns out that if you have a matrix A and you get it into an echelon form, both of those matrices will have the same row space. And so you could use the pivot rows from the echelon form to form a basis for your row space, or you could use the pivot rows from your regular matrix A and use those as a basis for your row space. It actually doesn't matter. That's a little subtle difference between row space and column space. That all being said, suppose you're handed a matrix and you're asked to find the row space of that matrix. Remember, the row space is the subspace spanned by the rows of that matrix. So if you really want to be lazy, you could steal those rows, write them as column vectors, and say the span of those vectors creates the row space of A. And remember, the span is always creating a subspace, and in this case, it would be a subspace of R5. But let's suppose that you are forced to not be so lazy. Suppose your professor says, listen, I get it that you could just give me the span of those 4 row vectors, which I always write as column vectors. However, you might have a text where the author wants to save some space. I don't blame them, paper's not cheap. So they write their column vectors, which are actually these row vectors here, they write them as ordered 5 tuples. However, I don't like to do that. I actually like to write my vectors as vectors, so I write all my stuff as column vectors. It's just a convention I like to stick with. Anyhow, back to this. If your professor says, well, I get it, that the row space of A is definitely the span of those rows, fine. But what if your professor says, I want a basis for that row space? Let's go ahead and approach that question. How would I create a linearly independent set of vectors that still spans the same space? Well, that's easy. We just need to figure out if any of these rows is a linear combination of the others. And the way you do that, well, good old row echelon form. And now you can see that one of the rows is definitely a linear combination of the other rows. So if you really wanted to tighten up those vectors so that you have a bare minimum number of vectors that still span the row space of A, you could use these vectors right here. And since these vectors are linearly independent and they span the row space of A, they would form a basis for the row space of A. Now, I did get ahead of myself there, to be honest with you, because there is a theorem we need to state and then prove to be able to actually use that. But I wanted to just put it on your radar because a lot of students see this and they just immediately know they can do that. But it's nice to know why you can do that. So we'll prove that, not in this video, but the next video. Before we get there though, let's prove a couple other quick theorems. If A is an m by n matrix, then the row space of A is a subspace of Rn. Remember, this is an m by n matrix, so therefore it has n columns. That is, each row has n entries, so it does make sense that the row space of A could be a subspace of Rn. To prove that it's a subspace of Rn, we just have to have a couple of vectors and a scalar multiple, and we'll take a scalar multiple of one vector, add it to the other vector, and show that that subsequent vector must also be in the row space of A. Let's go ahead and do it. We want u and v to be vectors in the row space of A, and we want c to be a scalar. Now remember, to show that this set of vectors is a subspace of Rn, we just need to show closure under vector addition and closure under scalar multiplication. Since the row space of A is the set of all linear combinations of the rows of A, and since u and v are both in the row space of A, then u is just a linear combination of the rows of A, and I've denoted that this way. This is the first row of A, second row of A, and so on and so forth until you get to the mth row of A. And these coefficients d1, d2, all the way to dm are the weights of the linear combination that creates the vector u. And of course the c is just a scalar multiple in the front of both of those. And v is also a linear combination of the rows of A. So when you add those two vectors up, cu plus v, you get this linear combination of the rows of A. That is, the sum of cu and v is in the row space of A. Because again, cu plus v is a linear combination of the rows of A. Its weights are cd1 plus e1, cd2 plus e2, all the way to the end there where you have cdm plus em. Now honestly, that proof could be streamlined a bit more, but I just want to showcase it a little more obviously than some other proofs would do. And I should give you some fair warning, the rest of this video just is a group of theorems that we'll need in the future. This one is pretty much the easiest of the group because all of our spaces, as far as column space of A, null space of A, and now row space of A, they are all subspaces. The word space is in the name, so I guess they must be subspaces, which are also vector spaces. However, there are some theorems here that, while they are seemingly obvious, they do require a little bit of investigation. Not much though. The row space of A is the same as the column space of A transpose. Now this proof is incredibly fast. The row space of A is defined to be the set of all linear combinations of the rows of A. Okay. However, the rows of A are the columns of A transpose. Again, okay. Thus, the set of linear combinations of the columns of A transpose, which is also known as the column space of A transpose, must be the same as the set of all linear combinations of the rows of A. Because again, rows of A, same as the columns of A transpose, so the span of those two sets are going to be the same set, and so the row space of A has to match the column space of A transpose. Very, very fast, and actually I do think this is something that most students pretty much get right away. Like I said, still have some theorems to go, only 2 left. Actually 1 left because I combined 2 into 1 in this video. This is known as Theorem 13 in the text that I use. If the matrices A and B are row equivalent, then their row spaces are the same. This is actually what I used in our example early on to showcase that we could find the basis for the row space of a given matrix by getting our matrix into row echelon form. So I sort of used this theorem without having permission to use it at that time. So again, the row space of this matrix A right here, according to Theorem 13, will be the same as the row space of an echelon form of that matrix, which is this form right here. So this matrix, which I'll call B, has the same row space as the original matrix, and that's why I went ahead at that point and said, well, guess what? If the row space of A is a span of the 4 original rows in A, well, let's get that matrix A into an echelon form so that we can minimize the number of vectors in that set and thereby create a basis for the row space. And that's what we did right here. But again, we did this without permission. We didn't actually have the theorem yet. The second part of the theorem states that if B is an echelon form of A, the non-zero rows of B form a basis for the row space of A in addition to the row space of B. Well, again, we actually kind of abused this in that example. So let's go ahead and just prove both of these parts so that from this point forward, we can go ahead and use this theorem to our heart's content. So for the first part, we're just going to suppose that A and B are row equivalent. Then B is obtained from A by using row operations, and vice versa, by the way. Another way of saying that is, if you multiplied A by enough elementary matrices and the correct elementary matrices, you would arrive at B. But let's pretend as though you started with A and you performed some elementary row operations to arrive at this brand new matrix B, or a brand new looking matrix B. All you've basically done is performed a bunch of linear combinations of rows of A. You've added row 1 to row 2, or maybe multiplied row 2 by a number 5, or something like that. That is, the rows of B are linear combinations of the rows of A, and technically vice versa. Well, if the rows of B are linear combinations of the rows of A, and the row space of A is a set of all linear combinations of the rows of A, that implies that the rows in B are actually in the row space of A. Therefore, the row space of B is a subset of the row space of A. However, each of these statements, I hope you observed, I was saying and vice versa. That is, if A and B are equivalent, you can create B from A. So you could have started at B and ended up at A. And that would mean that A could be obtained from B using row operations. So I will tack on to this now my official statement of and vice versa. Therefore, the rows of A are linear combinations of the rows of B. So I will tack onto that sentence the statement and vice versa. Hence, the rows in A are in the row space of B. So again, I'll tack onto this sentence and vice versa. Thus, the row space of A should be a subset of the row space of B, and vice versa is what I will tack on here. So the row space of B is a subset of the row space of A, and the row space of A is a subset of the row space of B. Therefore, those two row spaces have to be the same. There we go. That's a really kind of nice, interesting way to do that proof. It's full of stuff that feels like bijections. They're not really bijections, but they feel like they are, right? So suppose that A and B are row equivalent matrices, right? Then B can be obtained from A, or A can be obtained from B using row operations. Therefore, the rows of B are linear combinations of the rows of A, and likewise the rows of A are linear combinations of the rows of B. Hence, the rows in B are in the row space of A, and the rows of A are in the row space of B. Therefore, the row space of A and B must be the same. By the way, this very first part of this theorem is stating that the row space is invariant under row operations. So you could do as many row operations as you want on the rows of a matrix. Its row space will never change. That's kind of nice to know. Now for the second part, if B is an echelon form of A, the non-zero rows of B form a basis for the row space of A, as well as a basis for the row space of B. I'm gonna break this ink up a little bit, and I'm not gonna use the matrix lettering B here because I want to introduce a new notation, or at least it could be new. It depends on what textbook you're using. We're gonna let A sub ref be an echelon form of A. That's a very common notation, just means you were given the matrix A, and A sub ref is an echelon form of A. Remember, there are an infinite number of echelon forms of A, so A ref is not a unique matrix. One thing we know for certain, if you get A into an echelon form, the collection of non-zero rows of A ref are linearly independent. Moreover, from the first half of this theorem, because A and A ref are row equivalent matrices, the row space of A ref should equal the row space of A. Now remember what we're trying to prove here. We're trying to prove that A ref has rows that will form a basis for the row space of A. To form a basis, you need your rows to be linearly independent, and you need your rows to span the space. Well, because we have the linear independence part already taken care of, and because the row space of A ref is equal to the row space of A, not more than, not less than, but exactly the same, we know that the rows in A ref, the non-zero rows that is, must span the row space of A. We have the span down, we have linear independency down. This implies that the non-zero rows of A ref form a basis for the row space of A. That's pretty nice. It's actually pretty fast, right? So this allows us to take a matrix that's been handed to us, put it in an echelon form, and we've found the basis for the row space. And this is going to get us to a technique or a tactic for finding the column space, the null space, and the row space of a given matrix pretty easily. However, we've reached the end of the road on this video, so I certainly hope it's helpful for you, and I hope you have a wonderful day. Be a very kind human being.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook over affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Just listen close, don't talk too much that isn't cold. Sure, you may really hurt inside. It doesn't justify you to speak too loud and cry.